That was good.
I was like, huh?
I almost won like twice. I couldn't bring it home because I was too intoxicated to do so.
So I was going to give a quiz today.
And you still are.
And what do y'all think? Y'all want a quiz? Next class. All right, I'll give you the weekend, but don't complain on Tuesday. Or wait, sorry, never mind. We don't have the weekend. It's don't complain on Thursday that, you know, oh man, it's like a couple of days before Halloween. He's giving us a quiz. So we'll start class with a quiz next time. All right?
Fair warning.
Okay, you're warned. So last class we finished up, we were talking about what?
Shell method.
I started bringing in this idea of the shell method, and I had a couple of students ask me questions after class about the shell method. So I thought I would show you an animation that kind of helps us see, I think, a little better. And I'll ask Vanessa to kill the lights in just a second. Let me just remind you of what the shell method allows us to do. In the shell method, actually, the word comes from the idea of what are called cylindrical shells. Cylindrical shells. So what we do is we take something where, let's say the region that we're trying to wrap around is this region in here. Now I only have one, well, you could look at this as being two functions. There's a function on top and a function on bottom. Here the bottom function is just y equals 0, which is the x-axis. If I wanted to wrap that around the x-axis, I would use washers, right? The method that we learned. And that would be because the rectangle we'd be wrapping around would be perpendicular to the axis of rotation. But if I want to go around the y-axis, what's the trouble that I would have run into here? If I try and wrap this region around the y-axis, what would be the problem? My rectangle would have to be horizontal. And so if I draw that rectangle, the right edge and the left edge come from the same curve. And therefore, you can't do like an f minus g if it's the same curve, because that subtraction should give you 0, and it won't work, right? And there's no way I can rewrite this curve as a function of y to do it sideways. So if all we learned in Cal 1 was the method of washers and, what was it? Washers and discs, right? They're the same thing kind of, but if that was the only method we ever learned, then we could not rotate this around the y-axis, right? Agreed? That's where this comes in. So Vanessa, please. So I hope you can see here. Oh, come on. What's going on here? Okay. Why is this one not moving? Right, so as you can see here, if we look from the side, do you see that blue thing is like the curve I just drew, kind of? If I want to wrap it around the y-axis, what I do is I cut it up into a bunch of rectangles. I still don't know why this thing won't go back. Huh. Interesting. Well, if I take each of these rectangles and get more and more of them, if I wrap them around the y-axis, do you see how they swing around? And I create all these cylinders. Now, they're not coming out towards us. Maybe I can do another one. See if this one works any better. Can't change the angle. I don't know what's going on. Let me try this. Ah, I think that's the problem. There we go. Okay, that's what I was looking for. Okay, you see them? As I wrap these around the y-axis, they swing around like this. So you won't let me do it when I do that. That's what it is. All right, so there they are. Yes, you see them? That's half of them. Imagine they went all the way around. Each one of those vertical rectangles, right? So I wrap it around. Each one would create this cylindrical shell. And what we determined last time is remember we cut that open and laid it flat, and we came up with a formula for this volume wrapped around. Anyone remember what it was? It was 2 pi integral a to b of x times f of x dx. Right? So should I review where this came from, or are you okay with this? All right? I'm about to redo it. I'm going to redo the whole formula for a more complicated scenario than this, but that was kind of what I started talking about with shells. All right? So let's see now if we can adapt this formula to a more complicated region. So let's take a minute to draw two functions that are functions of x but cannot be drawn as functions of y. So how about we do something like this. And then below it, another function here. So I'll call this one g of x. The red one is g of x, and the blue one is f of x. Does everyone agree those are functions of x but not y? Yes? Those are both functions of x but can't be written as functions of y. Mm-hmm. All right. Now, if we want to take this region bounded by those two, and we want to wrap this region around the y-axis like this. Oh, well, you know what? Let's not do y-axis. Let's get more general than that. Let's go around this line over here. What would the equation of that line be? X equals something, right? A number? It could, in this case, x would be negative, right? It would be x equals like -2 or something. But does everyone agree that this would be some number? X is a. So if I go to try and wrap this rectangle around, this one right here, some arbitrary rectangle, then when I wrap it, I get the cylinder, don't I? Let's draw that cylinder. That's what it looks like, right? Does everyone see it on the paper, or like on the page? You know, it comes around like this, goes back, something like that. Right? You'll see that? I just don't want to clutter up my drawing, so here it is. What we did was we cut this open, right? We snipped it, laid it flat, and got the volume of this boxy looking thing. So we needed to know the height. What's the height of this rectangle? It's the top one minus the bottom one, right? The f function minus the g function. That's how tall this is, yeah? So this height is f of x minus g of x. So this is already different than our other formula, because when I did it initially last class, I was only dealing with one function. The bottom was the x-axis. This time we have a different bottom function. Okay, how wide is this little sliver? That's dx, right? Because that came from the width of that piece, dx. And then the length of this thing, we said, was the circumference of that circle, right? When you took it and laid it open, it was the circumference of this was the length of this. So the circumference is always 2 pi times the radius, isn't it? So we need to know the radius, don't we? Yeah, so let's see. This is going to be where things get tricky. Last time we said that the radius was just x, didn't we? That's where that x came from in that formula. But let's think about this. The radius is the distance from the center out to the edge, right? Okay, so that's from this green dotted line out to our rectangle. What we all need to keep in mind is that the distance from the origin to our rectangle is always x. Because we're letting x vary, right? X is going to vary between two numbers, a and b, isn't it? We're going to slide that rectangle back and forth by letting x go from a to b. So this distance from here to the rectangle is x. But the distance from that rectangle to the green is not x, is it? It's actually x plus whatever this distance is also, right? In this particular problem, a would have been a negative number, wouldn't it have been? Would I put like -2 here? No, it's a distance, so what would I put here? The 2, right? Understand? So this is actually going to be, in this problem, I'll put absolute value of a because that will make sure it's positive, right? But I'm looking for a general formula. So what I want you to do is just visualize that the distance from here to the rectangle, we're just going to call it r, all right? Radius. But I'm going to put a little subscript x there to remind you that that radius will always include x in it. X will be in it, but it might be just x, it might be x plus 2, it might be x minus 2. It just depends on the geometry of the problem, the setup. All right? So if this part right here becomes 2 pi and then some radius that's a function of x, then my volume of this is just this times this times this. And then we add them all up, right? Which means we bring in the integral. We go from a to b. We're done. So the volume of that solid of revolution would be 2 pi. That will always come out. A to b. And then instead of me writing x f of x like we did last class, I'm going to put r sub x. That's the radius. And then f of x minus g of x dx. And that's the big daddy formula for cylindrical shells. Any questions on where any of that comes from? Sure? All right, we should do an example. Yeah? Let's do, how about this? The region bounded by y equals x squared minus 1, y equals 1 minus x squared, rotated about x equals 4. Find the volume. So we have two parabolas, don't we? And we're going to take the region bounded by those two parabolas and we're going to wrap it around a vertical line x equals 4. So in the past you thought, okay, if I'm ever going to wrap around a vertical line, you'd think, okay, what I'm going to need to do is write these as functions of y so that I can get my rectangle to be perpendicular to my axis of rotation. But with shells, we don't need it. All right? So I'll start with the drawing. And I'll go quickly through the drawing because I'm hoping you all know how to graph those two. X squared minus 1. This parabola opens up. It's been moved down 1. That's y equals x squared minus 1. Agreed?
Yes.
All right. And then 1 minus x squared is parabola. It's opening down, but it's been moved up 1, and so it's kind of like the reflection of that, isn't it? Over the x-axis. It's this. Our axis of rotation, Vanessa, would you mind turning the light on? I'm sorry to interrupt you. Our axis of rotation is over here at x equals 4. I'm kind of out of room, so I'm just going to put it right here. Is that right? That's my axis of rotation. Are we all clear on why it is I cannot do horizontal rectangles? We're all clear on that? Okay. Yes? Zach? I didn't hear what you said. All right, so I'm forced to do a vertical rectangle if I'm going to rotate this region, right? So to do that, I'm going to pick some arbitrary rectangle in here, right? In the formula, I need to know a top and a bottom function, don't I? Which I've got. I didn't write the blue one. But I've got the top and bottom, don't I? This one is y equals 1 minus x squared. So that should be, I hate these markers. That should be pretty clear in our formula. Bless you. Let it go. I'm going to write down the formula up here so that we can refer to it. Did I put the dx on the formula? Yes? Okay. I don't remember doing it. All right, so right now we have the f of x and we have the g of x, don't we? The top and the bottom. All right, so the only thing really left for us to find that's going to take some work is the radius, which is the distance from what? Close. Distance from the rectangle to the axis of rotation. All right? So we need to find the distance from the rectangle to the axis of rotation. This is r of x. The one thing we do know is the distance from the origin to the rectangle. The distance from the origin to the rectangle should always be what? That will always be x. Okay, from the origin to the rectangle is always x. So if from here to here is x, and from here to here is 4, then this has to be what? 4 minus x. Right? So if, like, the distance from here to here, let's say that that was 1, and the whole distance is 4, then this would have to be 3, wouldn't it? It's the same principle. All you're doing is you're taking 4 and subtracting this value. So this r of x must be equal to 4 minus x. Does anybody have a question as to how I got that number, or how I got that expression? All right, so now we're ready. You just plug everything in. We're done. So this is equal to 2 pi. Do you know our limits of integration? A and b here. -1 to 1, right? That's where the two parabolas hit each other. And we're talking about x values, right? Not y values? Because we're integrating with respect to x. So it goes from -1 to 1 just by inspection. Because my graph was pretty good, I'm pretty confident that's where they hit each other. If I wasn't confident, what would I have to do to figure out those values? Set these equal to each other, right? But I can tell it's -1 to 1. The radius, which I write, what, 4 minus x? Think I need that in parentheses? Absolutely, have to have that in parentheses. And then your function of x minus your function f of x minus the g. So f of x was 1 minus x squared minus the bottom function, which was x squared minus 1 dx. Now I kind of have like a lot of parentheses in here, but I'm only doing that to be sure that you distribute that negative properly. All right? So let's clean this up. What does the integrand, what does the inside of that parentheses become? So 2 pi integral -1 to 1, 4 minus x. What is this? Is it just negative? Let's see, 1 minus plus. So we should have 2 minus 2x squared. Is that right? No? This becomes 1 minus x squared plus 1. 1 plus 1, right? So 2 and then -2x squared. And then we would just multiply these out, right? Just FOIL them out. And then you'd have polynomial, and you integrate term by term, and you're there. Okay? Seem easy enough? All right, now let me just, since we have the picture up here, let's do one more problem using the same exact picture. Let's rotate it around a line over here on this side and see how the R of x changes. So how about we repeat the problem, but this time about x is what? What do you want to use? Negative 4? Fine with me. Now what you're never going to face, I would never do this to you, is putting the axis of rotation inside the region. That would cause a problem. All right, so don't worry about that. It's not going to happen. So now, I'm going to come over here and let me draw this. I think I have another color in my bag. Thought I did. I need to go invest in some colorful markers. There we go. It's probably going to look exactly the same as that blue right there. It's a little different. So negative 4. So different problem, same rectangle wrapped around. So we need to know the only thing we really need is the R of x, right? That's the only thing in the problem that's going to change. So distance from the axis of rotation to the rectangle, right? This time would be what? Plus, right? This distance from the origin to here is 4, right? As a magnitude, the distance is 4, and then you have to add the x. So 4 plus x. So all it would do is change that right there to a plus. That would be the only difference in the problem. Understand? Okay. So remember, on your test, I'm not going to be asking you to take every single one of these and evaluate them, right? So what happens if I look at your formula and I said go around x is negative 4, and you have that up there? I mean, you're going to miss a lot of points on that. You can't come back to me and, well, it was just a sign. Well, I'm not asking you to do all the work. The most important thing is this. So if one thing is messed up, that's a big deal. So make sure you get your good drawing and take your time. All right, that's shells. Do we want to see any more of this, or are you okay with this?
Sir, can you go over the R of x when you change it again?
Okay, that thing that we wrapped around, right, this right here, we need to know the distance from the axis of rotation to this edge, because that cylinder comes from wrapping it around that dotted line, doesn't it? Our cylinder is created by this rectangle. So I want to know the distance from here to here, right? Okay, that's what I call R of x. I know that this x value is negative 4, so the distance from here to here is 4, right? That's 4 units, 1, 2, 3, 4. But then the distance from here to my rectangle is always x. So the total distance is the 4 plus the x.
What if you chose your rectangle to be elsewhere then?
Okay, well, I was wondering if anyone was going to ask me that. It will still work. Okay, so look, do you agree right here with my rectangle chosen this way, the x value is a positive number? Yes? Nope, it's not an absolute value. So check this out. If you just happen to draw your rectangle over here, right? It's going to be a little bit confusing to get this when you try and draw it, or when you try and come up with the formula, because you have to now realize that your rectangle is to the left of the origin, which means your x values are negative, aren't they? So if I'm looking for the distance from here to here, right? You would say, what? This distance is what? 4, right? And then you'd be taking away this x, wouldn't you? But x is negative, isn't it? So what happens when you take away a negative? You add. So you actually would come up with the same exact formula that I come up with my rectangle on the other side. So I'm glad you asked. here's the rule of thumb. Always draw your rectangle making x positive. So that way it's a little easier mentally to deal with. You can, as you can see the way I did that, I had to keep in mind x was negative, and then subtract the negative means adding. So if you don't want to deal with that, just always draw your rectangle on a positive side.
What if you put it in the middle?
In the middle?
Yeah.
Where?
Right in the origin.
At 0?
Yeah.
Well, then it would just be 4, wouldn't it? But see, the thing is, your rectangle moves, doesn't it?
Yeah.
You never get to like stop it from moving. That's what the integral does. It adds up an infinite number of them. So if you let x be 0, right? Think about the formula we have here. I'm going to change it to a plus. Think about the formula we have. If x is 0, that would give me this rectangle, right? What's the distance from here to here if x is 0? 4. Okay, what if x is 1? What's the distance from here to here? 5, and that's what I would get here, right? What if x is negative 1? What's the distance from here to here? 3, and that's what I would get here. I don't know if that answers your question. It's variable. X moves. This rectangle is going to float back and forth between negative 1 and 1. We just need a general formula that defines that distance. Our R of x function, no, our range is negative 1 to 1. That's the range that we have on x.
I meant from bound points from end to end.
Yeah, it's going to give you the two ends. When x is a, we should be here, and when x is b, we should be there. Yes?
What if we were to move the whole, both functions in the first quadrant?
Mm-hmm.
How would we do that? Would we do like from 4 to the origin or to this?
You mean if this whole region was over here, right? Then the distance from here to here would be 4, and the distance from here to your rectangle would be x. So you'd still have 4 plus x.
Oh.
We kind of opened Pandora's box there a little bit because you have to be a little bit careful with this rectangle and what its x value is. Because if it's negative and you subtract it, you really are adding. So would you like to see another example, or are you okay? You want to do another one? Okay. I've never really been too satisfied with the problems in the book for this section. So we'll just set this one up. We won't actually do it, okay? We'll set it up and we won't do the integration on it. So what about you have the region? The region is bounded by y equals natural log x, and then y equals e to the x minus 1, and then x is equal to 1, x is equal to 3, and you want to rotate this about x equals 6. So this is the region. This is where you want to rotate it. So let's look at the picture first. Do we all know what natural log of x looks like? Of course, right? Where does it hit the x-axis? At 1. And it goes like this, right? It goes like that. Well, that kind of doesn't grow quite that fast, but is that okay for this purpose? You know what? Let's make this. Might have to bring the e to the x down a little bit. Let's make it e to the x minus 4. Because we all know e to the x looks like this, right? Yeah? I'm just going to bring it down so that it's a what, instead of here, it's 1, 2, 3, 4, so like this. It's gonna go like this. Yeah?
So would there even be a problem if the graphs weren't touching each other?
No, that wouldn't, because I gave you these. Right? So we would have started at 1 and ended at 3.
So there's never anything that says two graphs that just don't touch each other? That's
Like, they don't have to intersect in order to find the area in between them.
They don't have to intersect to find the area between them as long as someone gives you bounds on the x's. Yeah. If I didn't give you bounds and the functions never intersect, there is no region enclosed. So it would be a dumb question. It would be like, you know, I don't know. It would be a dumb question. I guess, no, it would be me asking a dumb question of you. You know what I'm saying?
It would just be nonsensical.
That's right. It would be, yeah. Okay, my only concern here is that, that these hit each other before 3. Because I'm supposed to also put what, x equals 1, now that's here, right? And x equals 3, but where's that? So how could I determine if these hit each other before 3 or not? You do what? Plug in 3. Okay, I'm going to plug 3 in. What do I get when I plug 3 into this? It's e to the 3rd power minus 4. What's natural log of 3? Yeah, so look, what's bigger? Natural log of 3 or e to the 3 minus 4? Which one is bigger? E to the 3rd power minus 4 or natural log 3? We'll check on your calculator then. E to the 3 minus 4 is bigger? That means that 3 is over here, isn't it? Because look at my graph. The e function's bigger than the natural log. So 3's got to be over here. It can't be in here, right? So don't we have to figure out where they hit each other then? Yes? That's not going to be, I don't think we're going to be able to solve that problem.
Should we just map ourselves into a corner?
Yeah, a little bit, but it's okay. We'll fix it with, we have 2 options. We can either try and get a solution to this and ask Wolfram to do it, or we can move this point over to make it be to the left of this. So what do y'all want to do? Just move the point over and just move that. So what number would work? Does 2 work? Do 2 in here. Do e squared. I better get my calculator out. What's e squared minus 4? 3.4. What's natural log of 3? 0.69. 0.69?
Yeah, natural log of 2.
Oh, we plugged in 2?
0.69.
Okay, so that's not going to work? Got to get closer. We can take off completely, but then don't we need to know that point?
Yeah, we can ask Wolfram.
Set them equal to each other? You want to do that?
Yeah.
All right. We'll take x equals 3 off. So let's solve it. Here, this problem was just supposed to be one more example, and I screwed it up. All right. Let me solve. Can you solve that easily? E to the x minus 4. Uh-oh. My program's having problems solving this. Okay. Let's start over. Let's not move it down. Get a new drawing.
Wait, so Wolfram Maths can do it?
My Mathematica couldn't do it, which is Wolfram's brains. So probably not.
Maybe Newton was a crack.
I'll just leave it this way. Just do e to the x natural log x 1 and 3. Natural log x looks like this. That happens at 1. E to the x looks like this, right? X equals 1 is here. X equals 3 is here, yeah? The region's enclosed by those three? Or those four curves? Axis of rotation. I'll give you a second to catch up. While you're doing that, I'll label these things. What was that? I draw my axis of rotation, right? Which is over here at 6. By the way, on your exam, I will not tell you you have to do your volume solids with any particular method. So if you're doing a problem and you think shells is better than the other way, then you're free to do however you want. All right? I won't force you to do one or the other. All right, so here's my rectangle. That rectangle is going to rotate this way. It's going to be parallel to the axis of rotation, which means I'm using shells, right? Shells is always parallel. And so I need to know a top and a bottom function. I've got those. I need to know the distance from the rectangle to the axis of rotation, right? R of x. Which would be what? Six minus x. Because the distance from the origin to my rectangle is always x. And x is positive, right? So, and then the distance from here to here would have to be 6, take away that x. My integral will go from where to where? X value of 1 to the x value of 3. That entire distance was 6. 6, take away that x, and that's this piece right here. Bless you. Okay, I hope that helped a little bit. That one? I mean, it's pretty much the exact same problem that we just did, different functions. So 2 pi integral 1 to 3, that's the bounds on x, 1 to 3. And then I have my r of x, which was 6 minus x. And then the top function, e to the x minus natural log x dx. And you'd have to multiply that all out, wouldn't you? Let's multiply it out, just to see what we'd be looking at here. We get 6e to the x minus 6 natural log x minus xe to the x plus x ln x. I believe that's it. Do you agree with that? Could you integrate each of those? Antiderivative of 6e to the x is 6e to the x. Could you find the antiderivative of natural log of x? That's the derivative. We did it in class once. We used integration by parts. This one is definitely integration by parts, and that one's also integration by parts. It's an interesting problem.
Do you think we do, or there would be a bonus question based on not volume but surface area?
We're going to do surface area today. Yeah. All right, we good? All right, let me move on. We have another type of volume that we want to look at. And I think the best way to motivate the idea is to show you this little animation that I came up with. So, Vanessa, if you don't mind, let's kill the lights. And I don't think I'll put the camera on it. Movie time, yep. Where is it? Here it is. I was messing with the code before class trying to get this to work. This code, look at it, it's pretty nasty, huh? But I got what I wanted, finally. Here it is. Come here. All right, so this is the problem we were just looking at a second ago where we had 1 minus x squared. And we had x squared minus 1. And it created this thing like this, right? That's what we had. And what we did is we took that region bounded by both of them and we wrapped it around some vertical line, right? That is not what we're about to do here, right? Not at all. So what I want you to imagine is that, and listen to the wording of this. This region is the base of a solid, all right? This right here, the region bounded by those two curves, okay? Those, right? The region bounded by those forms the base of a solid. So above this region is some solid object, okay? Now let me give you some characteristics of this solid object. If you take a cross-section of this solid, does everyone see there's a solid sticking out at us right here? It could be a lot of different shapes, couldn't it? This particular one, if you take a cross-section that runs perpendicular to the x-axis. So I'm going to come in here and slice it like this, okay? Not like this. That would be perpendicular to the y-axis, wouldn't it? A cross-section that is perpendicular to the x-axis forms a rectangle where the base is the distance between these functions and the height of the rectangle is 1. Does everyone see what that is? Probably not, right? I mean, it's kind of hard to see. So that's what this is about. I'm trying to show you this in an animation. So what I'll do is I'll pick an arbitrary slice. That's supposed to be my slice coming through the solid, okay? And when I take a look at that slice from the side, it's supposed to be a rectangle. Does everyone see the rectangle? Where the base of the rectangle is the distance between the functions, and the height of the rectangle is 1. All right, everyone see it? So when I come over here, I don't want to write all the words I just said, where the base is a rectangle and the height is 1. I'm not going to write that all down. What I'm going to do is I'm going to show you how I would draw that here. So I go 3D. We did something like this last class, right? Because Ron was saying, no, it looks like it's going into the board.
Oh, it could go either way.
It could go either way, yeah. So I have a bottom parabola. I'm going to blow this up. A bottom parabola that looks like this. That's not very good. Then I have a top parabola, which goes like this. Okay, that's the thing laying on the ground. And what I did is I came in here with some arbitrary slice, right? And notice I'm picking a slice that's over here on the positive side, okay? That slice creates a rectangle where the height is 1. So from this I go straight up 1 unit, whatever 1 unit is. I lost my slice. There it is. And I get this piece there, right? If I slide this slice somewhere else, the rectangle is going to take a different shape, isn't it? What's going to change? The base, right? The base of the rectangle is going to change. So that's what happens in this animation. I can move, notice the height of the rectangle is always the same. So if I look at it from this point of view, notice the heights across the top are always the same, but the base is getting smaller. So you can see on this little slice at the end, coming from this side, it's very, very small, right? Base. If I take all the infinite slices, put them together, that's the solid. And we want to know the volume of it. So here's me putting everything together. You get that shape. Now notice you can see that rectangle move through the shape. See it? This shape, I want to know the volume of. Understand? All right. So we're going to do it just the way we've done everything else in this class with integrals. We find a formula for what it is we're trying to add an infinite number of these things up, right? If it's area, we found the little rectangle formula, and we did an integral on that formula. If it's a volume, we created washers, we added them up. If it was the shells, we did the shell formula, we added them up, right? So let's just figure out what the volume of one of these little cross-section slices is. So I need to add a little bit of width to this, right? How do I add width to the little slice? I make it how wide? dx, right? Which over here would create a little bit of width to this and give me like this little slab, wouldn't it? That little slab now has width to it, it's dx. So let's take that picture over here and figure out the volume of just that one slice. So I'm going to kind of draw it over here. We know this is what? dx. Do we know this?
1.
It's 1 because I told you in the problem the rectangle always has a height of 1. That's never changing. The only thing that changes is this piece right here, right? That varies. That actually depends on where we are, doesn't it? And according to our formula, I'm sorry, our picture, it's this distance here, isn't it? Which is, how did we always find the distance? We had a top and a bottom. F of x minus g of x, right? What's the f of x for us here? What's the top function? 1 minus x squared. What's the bottom function? X squared minus 1. So this distance from here to here should be the f function minus the g function. So what is f take away g? F take away g. Let's just do the algebra there. Didn't we do that earlier? Isn't it 2 minus 2x squared? That right there is this. Agreed? That's the dimensions of this little sliver. Now we multiply those three together, right? And that gives us the volume of that little sliver. So what's the volume of the entire thing then? Of everything, the whole solid. How do I do it? Integral, right? Because I'm going to add up all these slivers. From -1 to 1 because I'm going to be integrating with respect to x, right? And I can tell from my picture x goes from -1 to 1. 2 minus 2x squared dx times 1, but I don't really need it, do I? So you see this formula, that's it. There's nothing more to do. There's no 2 pi in there. There's no pi, r squared. We're not doing washer. We're not doing a disk. We're not doing a shell. We're coming up with a formula for one slice, and we're adding them all up. That would be pretty easy to evaluate, wouldn't it? Any questions? Let's try something else. Let's do the same exact region, all right? Same exact region. This time, I'm going to tell you that when you do a cross section, right, like this, do a cross section, that it forms a square. That's it. Forms a square. So what's the difference? Let me draw that a little bit bigger.
It's not they're not curved, they're just straight lines.
Okay, so like on the one we had right here, didn't we say that those heights were always the same?
Yeah.
Right? Because it was a rectangle, it was always 1. This time, the heights are going to get smaller as we move further out because the base is getting smaller. If they're squares, the base and the height are the same. So let's see if we can get our heads around what this thing's going to look like.
Would it be f of x minus g of x equals 1? Would you equal it or set it equal to 1?
No, you don't need it.
That's what I was thinking.
Look, those are all squares, right? Notice how the base is getting smaller as I move out to the edge. But if it's a square, that means the height has to get smaller. And so I get down to almost a little point where it pinches off there, right? In the middle, it's the biggest it will ever be, right? And then on the other side, it does the same thing. It shrinks down. So let's take a look at that one. That's the shape. Very different than this shape, right? That's rectangle above. This is a square above. Got it? Okay. So we have the same two functions like this. The reason I'm writing it all down here, up here, is because, again, I want you to see, like on a test, how you would, like, what is the work I'm looking for? Well, I want you to do this. I want you to label these graphs. Y equals 1 minus x squared. This one here, y equals x squared minus 1. You would show me a typical slice on this thing, right? Your slice comes through. Go ahead and lay that slice on the ground. Is that what it would look like? Notice I'm not even drawing the axes anymore. I'm just laying that slice on the ground. What shape does it form with that slice? We said a square, right? So however long this is how tall it is. So I've got to go up, over, down, something like that. But it's a square. How wide is this thing? Dx. How about that piece? That's f minus g again, isn't it? Which for us, we've already done this. It's what? 2 minus 2x squared. But since it's a square, that's what the height is also, right? So this is 2 minus 2x squared. So what's the volume of this one slab? This times this times this, right? Add them up forever, infinite number of them. So our formula is just going to change a little bit, isn't it? Just a little bit. Formula is going to be integral -1 to 1. It'll be 2 minus 2x squared squared dx. Does that mean you could have just found the answer to the other one and squared that answer? And careful, yeah. If you just do the other one and then square the answer, it's different than this one, because this one you have to integrate the thing that's squared first, and that would be much different. You can check it yourself, but I guess what I was just asking you is this. This is more of an abstract idea. Is this true? In general, is this true? Take the integral of a function from a to b. Take that numerical answer and square it. Is that equal to, question mark, the integral from a to b of the function squared? No, it's not. This is the area under the function, right? F. Whatever that area is, if we square it, is that equal to the function squared area underneath? No, not in general. All right, we're going to keep moving. What if what I said was these cross sections formed circles? And the circles have as its diameter the base of the region. So same picture. But this time the cross-section forms circles where the diameter is the base of the region. So take this slice that is perpendicular to the x-axis, lay it down on the ground, and what you know is that this is the diameter of a circle that is formed. So can you draw a circle like this? And then give it some thickness like that. Do y'all see it? It's like a disc, isn't it? But we're not going to use the method of discs. We're just going to come up with a formula for that. Right? Mm-hmm. But it is a cylinder, and we do know how to find the volume of a cylinder, don't we? The volume of a cylinder is pi r squared h. Do we know the height of this cylinder? The thickness of the cylinder? Dx. The only other thing we have to resolve is what? Pi r squared h. So we need what r is, right? We need the radius. The radius is the distance from here to the edge, isn't it? Is that f minus g? It's half of f minus g, isn't it? F minus g is the whole thing, right? You want halfway. Could I have just used, instead of saying half of f minus g, could I have just used f?
On this one.
On this one only because it's symmetric, but in general, no. This one you could have, but in general, f and g don't have to be mirror images of each other. So this distance will be half of the f function minus the g function. Do you agree? Yeah? Everyone's okay with that? Mm-hmm. Which for us, in this particular problem, we had already done f minus g several times. It was 2 minus 2x squared. So for us, this is just 1 minus x squared. Yeah. Half, half. So what is the volume of this sliver here? It's pi, right? Pi times this squared times the height. And then we need to add them all up. So my integral. The volume would be integral -1 to 1. Pi times, I'll bring the pi out, 1 minus x squared, squared, right? So it was pi r squared times height. Then you multiply that out, integrate, you're done. Last one. Oh, I never showed it to you. Circles. So there's a circle moving through, and there's the solid. Right? We can find the volume of that. What if I said instead of circles that they were semicircles? It would be half of this, right? And that would work this way. You would just take half that volume if they were semicircles. So if they were semi, all you do is just put a half in front of this. All right? Last one. Last one. Same region. Cross sections that are perpendicular to the x-axis form equilateral triangles where the side, the base of the triangle is the distance between the two functions. Equilateral, y'all know what equilateral means, right? All sides same length. So